Welcome to another RDWorks Learning Lab. Today, hopefully, we're going to unravel a few more mysteries about graphics and engraving. Just recently, somebody sent me an ROD file, and I was rather puzzled at what I saw. It was a very nice picture, low resolution, not running at too high a speed, but it had been dithered. Now, as well as dithering the picture to produce black dots on a white background, the program had also been set up with output direct, and we had a max and a min power set. Now, the output direct and max min power would indicate an attempt to do grayscale engraving. There seemed to be a logical conflict between having a black and white or black dots on a white background dithered picture, which is basically a binary picture, and then trying to process it with grayscale, because there are only two levels in that picture, black and white. My first reaction was, this is silly. But my second reaction was, well, maybe it's not that silly, because just possibly, remember when we were talking about RDWorks messing with my pictures as I brought them in? RDWorks somehow adds some extra shades of grey to it when it displays it to you. Now, we never saw those shades of grey because, to be honest, I was just using plain dithered parameters. I was not using grayscale parameters. So just possibly those additional grayscale bits that are shown in RDWorks, maybe they are there, but I wasn't seeing them. So today what I'm going to do is going to experiment with grayscale, looking at these pictures to see whether or not there is any grayscale information in those pictures, because now we know from our oscilloscope traces how we can see grayscale. Okay, well, here we are in RDWorks, and I'm just about to import this coloured 600 pixels per inch bitmap. And as we anticipate, it comes in grayscale. We'll just go into the bitmap handle, and we shall first of all set these to 0. We can reduce that 600 to 120 because I don't want too fine a resolution picture. And now we get the opportunity to dither. Now we've got several options of dithering down here. One of them is dot graphics, which is the one that we have been using. So let's just use dot graphics to start with to set the benchmark, and we'll apply to view, and sure enough now we should find that we've got lots of dots. But if we look closely, we shall find that we have actually got, if we can count those, and I have looked at it very carefully, it's very confusing, but I believe there's black, there's white, there's 2 shades of dark grey and 2 shades of light grey. So I think there are 6 colours in that picture. So we will apply to the main view. Okay. And here we are. We've still got all those pixels in there. I'm going to run it quite slowly because that's how I think that probably, certainly to be able to see what's going on, we want to run slowly. It's a matter of how fast we can run and still not destroy the quality of the picture. Is something we can find out later. It really doesn't matter what the power is I'm going to be using, because I'm not going to physically cut or engrave anything. But using these extreme values is going to help us to sort out what's going on when we look at it on the picoscope. This increment size here is wrong for 120 pixels per inch, but it doesn't really matter because I'm not going to actually do any engraving. So we'll happily say OK.
I've removed my lens and I'm firing my program down into a small container of water so that the energy doesn't get reflected off of my base plate or anything. So something I would advise you to do if you're playing with the machine like this, especially with the door open as I am. Right, let's see what we've got. Right, well, we've got roughly 50% power there. Although 50% power doesn't mean to say it's going to be 50% up the scale, but you can see that that red line is pretty high relative to 0, which is down here. Now, You can clearly see my dots switching on and off as it's attempting to produce the picture. We've only got one level of power and lots of dots. I'm going to change the parameters. This time what we're going to do output direct, and we're going to change the parameters to 10% and 50%. Okay, so what we can see on the screen here is our typical dot format with a constant red line across the centre, regardless of the switching that goes on for each dot or group of dots. Now, we're going to run the grayscale, and all we've done, we've got the same picture, which is supposedly a binary picture, and our anticipation was that RDWorks had added some grey in there, some six levels of grey. So what we might find here is if those grey levels are really there, we should see various levels of red. So let's go and check out whether those greys are there or not. Well, the answer is or not. So adding grayscale to a dithered picture does nothing. We will just change the time base just to see whether there is any effect, but I'm very confident there isn't. No, the red is not changing at all. So there's the answer to question number 1. RDWorks is actually fooling you when it puts those greys in, and we ask for a grayscale interpretation of that picture. There is no grey in that picture. Okay, so I've got to start again. So we put our bitmap handle around it, set the resolution to 120 again. This time we will dither it. Instead of dot graphic, which is what we did before, we will go for grayscale. It clearly tells me up here I've set it to 120 pixels per inch. I've dithered it, and it's grayscale. We've applied it to the view. We'll apply it to the main source file. Okay, now we'll set the parameters. In fact, this time we'll leave the parameters exactly as they were before, 10 and 50. And we've got our output direct, but this time we've got a grayscale image that we're playing with, not a black and white image. Okay. Well, that was certainly a big file. It took best part of 5 minutes to load into the machine. So let's run it and see what we've got. Well, here we go. Look, one single scan, and we're firing a value to suit hopefully every pixel. But that is truly a grayscale picture, because we've dithered it grayscale. So without changing anything except the form of the dithering itself, we've now got a grayscale picture, because we've got an on switch and an off switch at the end of each scan line, and for every scan line the current is going up and down, changing the power for every pixel. Now I've zoomed right in on this trace, as you can see here with this line, and we've got this little bit just here. Now you can see the individual pixels here, and so what I've done, I've looked at the time base at the bottom, and I've tried to work out what the approximate length of a pixel is. Now you can see that there's a bit of a slope here on each one of these, so it's not an exact science to get exactly where the step is. Now, we were running this program at 15 millimeters per second, and if I tried to find out how long it takes for 1 millimeter, that's a 50th of a second, which is 20 milliseconds. Now, we also we're running the program with 120 pixels per inch resolution. And if I want to calculate that back, I can find out that that represents 4.72 pixels per millimetre. Now if we divide 20 milliseconds, which is how long it takes to travel a millimetre, by 4.72, which is the number of pixels there are in a millimetre, what I shall find is that it takes 4.23 milliseconds for a pixel. Now, as I just mentioned, I've just done a quick check across the bottom time base, and these are the numbers that I've come up with on the step length. And if I subtract one from the other, I find that I get an answer of 4.2 milliseconds. Well, within my ability to estimate where that step is, I think we can see that what we're seeing on that trace are whole pixels. So at 50 millimeters a second, we can see every pixel resolution, which is great. Now the question I've got to ask is, how fast can we go before we don't actually see that pixel? And that's the next question I'm trying to answer, to try and find the maximum speed that we can travel at when we're doing grayscale engraving. Let's jump right up to something which is much more practical if we haven't got a huge amount of time to spend, and that would possibly be 200 millimeters a second. So we've still got a minimum 10% power and a maximum 50% power. Well, at 200 millimeters a second, let's stop that and see if we can analyse the trace. Maybe here, because it looks as though we've got some separation here. Yeah, we can see some steps there. Yeah, the slope is getting a bit vague. The step difference between them now is getting a bit less crisp. But at 200 millimeters a second, let's see what's happening. Now, using this previous calculation as a template, if we do 200 millimeters a second, then we're going to finish up with 5 milliseconds for 1 millimeter of travel. We haven't changed the resolution, it's still 120 pixels per inch, and therefore all we've got to do is to divide the 5 milliseconds by the 4.72, and what we finish up with is roughly 1.06 milliseconds per pixel. And the answer that I could see on the screen was roughly 1 millisecond. So again, it looks as though we're seeing complete pixels. Okay, we're now doubling it to 400 millimeters a second. So let's have a look, see what the results are at 400 millimeters a second. Well, we can see that that's roughly half the length that it was before. So let's zoom in and have a look to see if we can see any pixels here. We're going to see the best chance, I think, on these steep edges. There's a step there, maybe. So it might be doing something, but it's not displaying. I can't see any evidence of pixels there. Not at 400 millimeters a second. Yes, there's a general change in the pattern, but I would guess that from that pattern that the picture would start getting fuzzy. Okay, so 400 millimeters is too fast. Let's start it up and try 300 millimeters. Just stop it and sample that, or let's just stop it and zoom in on that. Yeah, we're seeing distinct pixels. So it looks as though we've got a limiting speed of about 300 millimeters a second, which is still pretty phenomenal for the system to respond that quickly. Yeah, 200 was 1 millisecond, so 400 would be half a millisecond, and we can't see steps, we can't see pixels at half a millisecond, but we can at 3/4 of a millisecond, which is 750 microseconds. Okay, so we've demonstrated that that is possible. The next thing that we can look at is that, yeah, we could actually improve the resolution of the picture if we wanted. For example, we could go to 300 ppi. But if we went to 300 ppi and we're limited by this 750 microseconds, then what we'd have to do is change the speed down to 150 millimeters per second to still keep 750 microseconds for an individual pixel. Now, we ought to be quite excited about this, but I'm afraid I've got to be a little bit practical, because two major problems exist with these numbers. What we've been concentrating on up to now has been the electronic signals that are passing between the controller and the high voltage power supply. Now, it's all very well to say that we're seeing a signal, a single pixel every 750 microseconds, but that doesn't mean to say that's what we should see out of the tube. So up to now, we've been seeing a 750 microsecond limiting period to see a single pixel. But of course, that's before it passes through the high voltage power supply. Without any knowledge at all on my part, let me guess and say that after that 750 microsecond signal has passed through the HV power supply, we may only be able to see pixels that are 1. And even then, they may not be like that. They may well be more like that. So they may well already get distorted as they pass through the power supply. Now, the next question is, who knows what we're going to see coming out of the tube? I have not got the ability to measure what's happening in that tube on the high voltage side, so there's no way that I can ever know for certain. Chip Williams has got kit that can do that, and he might be able to help me at some stage, but so maybe we can only see pixels if they're more than 1.5 milliseconds long. And even then, we can't really say what shape they're likely to be. We might be able to just distinguish between pixel steps, but not the length. Okay, so now we've basically doubled what we thought we had for a pixel time. And that basically means we're going to be limited to 150 pixels per inch at 150 millimeters per second. Or we could go up to 300 pixels per inch at 75 millimeters per second. Having knocked the top off that euphoria, we've got another hit that we might have to take, and that's all to do with, as we've talked about it before, the dot size that you can actually achieve. Now, the faster you run, the smaller the dot will be. But sadly, as you make the dot smaller, you make it less powerful because it's staying in one spot for less time. So consequently, the burn or the colour is less. This is becoming very complicated again. The only way to find out whether or not we've got something that's usable is to give it a try. But at least we know the zone that we can work in. So I'm going to run a trial at these maximum conditions. Okay, now I've just tried to run the file from here, and I cannot run it from here. It does silly things on the machine, like it scans and then it keeps offsetting and scanning in all sorts of different places across the machine. I tried getting onto a stick and that didn't work either. So the only way that I've succeeded in loading this file to the machine has been with the download. As you can see, I've got a download success now. We'll just take a sneak preview through the gap in the cover here. I would say it's probably quite dark, and I could probably reduce the power even more. I mean, it's already at 9 and 14. I think if I reduce it to 9 and 12, the only reason we can succeed with a photograph on an organic material is because there are different shades that we can get with the different burn depths or different burn powers. You can't do that on other materials such as glass, slate, acrylic, because they just do not have any variation of colour. They're a binary material. So you need to choose the material carefully if you want to do this. And I'm not even sure this is going to succeed, but we will give it a good shot. I think you can see that is pretty hideous. There's no detail there. The last time we tried this, it was on the light blade machine, and at that point in time I didn't know what I was doing, and it seems I do know what I'm doing this time, and it doesn't make it any better. And that was the result that we got the last time. That was just as fuzzy as this one was. Well, in fact, if anything, the eye on here is a little bit clearer than it is on here. But to be honest, they're both worthy of a trip to the dustbin. I think the conclusion is, don't go anywhere near Greyscale if you want a decent picture. The only way to deal with pictures is with dots.
Well, it seems that my little picoscope has not been a waste of money after all. It's actually been a wonderful tool for telling me how this machine works. It's helped solve problems that we could never find out by just looking at the end result. As I've proved several times, second guessing what the machine is doing doesn't really work. So I'm glad I've found a tool now that I can use to tell me exactly what's going on. And that certainly helps to define the boundaries of graphics work, what you can and cannot do, what you should and should not use. Greyscale was added to this machine, I think, specifically to get various depth control for 3D engraving, not for grayscale pictures. You have to have a specially prepared picture for 3D engraving. The whites stay near the surface and the blacks cut deep. Now, just as an example, her eyes, you don't want her eyes to disappear into the background. Her eyes are in the foreground. But that won't happen with 3D engraving. If it's black, it will be deep. So just remember that when you look at a photograph and think, I'll have a go at 3D engraving that. Well, I hope this has been another informative session. I've certainly learned a lot, as I usually do. This, again, was a first-time journey of discovery for me. I've not poked in this corner before. Well, you've seen that the end result is not good, but that's as much a success as something like this. Because at least we know that we can't go there. It set boundaries, and that's all we're trying to do. We're trying to find the boundaries of this machine, what it can and cannot do. Well, thanks again for your time, and I shall see you in the next session.